Power engineering, a single line diagram, shortly known as SLD, is also sometimes called one line diagram, is a simplified notation for representing a three-phase power system. The one line diagram has its largest application in power flow studies. Electrical elements such as circuit breakers, transformers, capacitors, bus bars, and conductors are shown by standardized schematic symbols. Instead of representing each of three phases with a separate line or terminal, only one conductor is represented. So single line diagram means representing a complete electrical system in one line. Okay, it will be including the transformers, generators, circuit breakers, bus bars, whatever things we are handling. Like when we have a building, we'll be having an electrical room. In this electrical room, we will be having main panel, sub panels. So all these are represented in single line diagram. Okay, and SLD flow analysis. Initially, the single line diagram provides a framework for the incorporation of different types of required information, such as incoming service voltage and utilization voltages required, electrical distribution equipment, ampacity on and short circuit ratings, overcurrent or short circuit protection, conductor types, that is cables or busways, and its sizes, cable length to determine the voltage drop, the transformer KVA sizes, ampacity, impedance and voltages, the generator KVA size and voltage, motor loads and voltage, and other power quality equipment such as surge protection device, power factor correction, capacitors, or uninterrupted power supplies. So in this particular SLD, whatever project we are doing, we will be preparing a single line diagram. So in this single line diagram, it will be showing the incoming voltage. For example, if you're having a load of 100 kV or above, you might have a transformer inside your building. So you will be having like 11 kV substation in your compound or inside the building. So the supply line coming will be 11 kV. So the transformer will be depending on our total load or the kVA, our transformer size will be 100 or 160 kV or above. So the incoming supply will be mentioned in the SLD, like single line diagram. 11 kV bar 433 volt is the distribution transformer step down voltage ratio. Okay, so the voltage you will be mentioning the voltage all over the single line diagram, and the short circuit protection and the ratings, like you will be mentioning an incomer breakers. Maybe it will be MCCB or ACB, or maybe vacuum circuit breaker. You will be mentioning the short circuit values, the ampere values, everything. And the conductor types, whatever conductors we are using. Maybe we will using a 11 kV conductor, like HT side conductor and LT side conductor. You will be mentioning the cable size and the number of runs and its insulation, everything. If it is a bus bar, you will be mentioning the bus bar thickness and width. Okay, and also you'll need to provide the voltage drop calculation. If the cable length is little more, like more than 100 meter, you might have to do the shorter voltage drop calculation in the SLD itself. Okay, then the transformer size, generator size, transformer protection, primary protection of the transformer, secondary protection of the transformer, and also the generator. Based on our backup load, the generator will be providing a generator, so it will be shown in the SLD. So you need to show where this generator is supply is going, like you will be providing a generator main switchboard. This generator main switchboard might be connected to the backup load that we require in the particular building. Okay, and the motor loads, the building will be having certain motors like lift motors, water pump motors, like and additional lift motors, everything. So you will be mentioning this as motors like synchronous motor or induction motor, and you'll be giving the protection rating and the cable size for all these motors, and its rating also you'll be mentioning. And the power factor quality improvement, like if the transformer is operating at 0.8 power factor, you can improve the power factor by providing capacitor banks. So you will need to mention the capacitor banks also. So SLD flow analysis includes all these details. Okay, so the life of a single line diagram, like how we prepare, how we start to prepare the single line diagram. A single line diagram may start out in the design development phase of a project as a basic concept. Other information can be added throughout the design cycle. It can then be copied and modified to create a number of alternative drawing showing different system approaches. Like initially, as the project design starts, we will be preparing like a concept drawing. So when we start this concept drawing, we'll have an idea about the number of distribution boards, the rough load, like the total load. You will be having an idea of total load. So you will be expecting a transformer of this much size. So further designing, the load might be changing as per the client's requirement or as per the new equipment schedule or the load schedule, the load might be changing. So initially, when we do this, we will be starting with a small concept drawing, like initially with some loads only. But as per the client's requirement, it will be changing. So you will get an idea how this is changing the physical parameters. Like if there is only one or two sub panel, the electrical room size will be according to that. So if the sub panels are increasing, the electrical room size will be changing, the transformer load will be changing. So accordingly, you will understand what all changes are coming in our single line diagram. That is, this permits the power system designer to analyze the impact of each arrangement on cost, redundancy, and the project physical space requirements. The system SLD takes on increasingly more importance as the project evolves through the design development phase. Input from other architectural, mechanical, plumbing, electrical, and fire protection professionals on the design team helps to better define the various equipment loads and develop the power system one line to another. Because when we start this concept design, we will be looking only for the purely electrical load, like lighting load, power load. We might have to coordinate with the HVAC people, like they will be having the air conditioning load with them. So they have to share the air conditioning load, then only we will understand what is the total requirement load for the HVAC system, as well as the plumbing also, and the firefighting. So after coordinating with this team, then only we can finalize the total load of a single line diagram. Okay. Then what is the importance of a single line diagram? It is important for the power system designer to ensure the single line diagram and the other design documents contain as much information as possible to assure that bidding contractors include all the correct requirements in their pricing. Errors or omissions on the construction contract documents can lead to expensive contractor change orders and project cost overruns after the contract is awarded. So while we prepare this single line diagram, you have to make sure that all the details are included in the single line diagram. Like the cable size, you have to mention the proper cable size, the circuit breakers, the current transformer, the potential transformers, all the details you have to include. If you miss something and it is actually needed, and the contractor will be bidding the quotation for the drawing which we have ordered, and that drawing is missing some important details. So he'll be putting the amount related to that drawing. So finally, when the client is having actual requirement, the cost will be changing. So it might overrun the total cost. So you have to make sure that while preparing the single line diagram, all details are included, everything. Okay. As the design process continues, coordination between the MEP design disciplines become more critical. If the design professionals are not synchronized on these changes, a previously unanticipated piece of equipment may be chosen or added to the project. For example, initially the air conditioning load was particular tonnage, for example, 100 tonnage. As per the client's requirement, this tonnage have been changed. Like it has been increased to 150 or 120 ton, which means the electrical load also changed. So if you are not coordinating with the newly updated load, it might cause some problems, like the circuit breaker size will be changing as per the new HVAC load, and the cable size will be changing as per the new HVAC load. So you have to make sure that you are following all the, you have to make sure you're coordinating with them, and you are updating them it in the single line diagram. For example, when an engineer had previously allocated a 250 ampere circuit breaker to feed that anticipated load, as a result of equipment change, a 400 ampere breaker must now be provided. The impact of this change can result in a contractor bid that does not include both the correct breaker and the correct cable size to feed the larger load. Okay, then finally, electrical equipment is subjected to environmental issues such as wet areas and may require specific enclosures types to be provided. Nomenclature on the single line diagram such as 3R or 4X adjacent to these items can clarify what enclosure type is to be provided. For example, if I'm taking a cable of AYFI, this is a cable code for aluminum cable. The conductor is aluminum, PVC insulation, steel strip armored, again PVC outer sheet. That is a cable code representation for an aluminum cable. So if I want A2HFI, A2HFI means aluminum cable, XLP insulation. So the insulation has been changed. So you have to select the insulation type according to the conditions where you are using this cable. It is exposed to the weather critical areas like wet areas, or you are using in a medical field where you are handling some chemical objects. So you have to make sure you are following correct insulations on these cables, and you might need armored cable if you are feeding it underground. So you have to mention the proper description of the cable. So if there is one run or two run, which means what you have, if you have two cable, you have to mention it as two runs. If you are having one cable only, you have to mention it as one run. So the proper description is very important in single line diagram. Okay, as an example, a note can be added clarifying that all NEMA 4X rated enclosures are to be of 316 stainless steel versus the less expensive 304 grade. The difference between these two grades is critical, as 316 stainless is far more resistant to salt water, sulfuric acid, and chlorides, and is preferred in several applications, including pharmaceutical manufacturing and wastewater treatment plants. So you have to make sure you're following the proper specifications of the equipments you have selected. Okay, then the system single line diagram is the common map that all the project document must reference and checked against to ensure consistency and avoid conflicts again after a project is awarded to a contractor. Distribution panel board schedules and specifications also need to include the correct information about the details such as enclosure type required. Like, for example, when you're sharing the single line diagram, you need to mention all the load details. For example, if consider an apartment building, 10-story apartment building might be having 4 or 6 apartments per floor. So it might be having total apartment like 60 or 50, like around 50 to 60. So the total load will be calculated based on the distribution board's individual load. Like you have 60 apartments, you have to take the load schedule of individual 60 apartments, and you have to consider a sub panel because you cannot directly connect this distribution port to the main panel. You'll be having a main panel, sub panel, then the final distribution board. So you have to give all the details of the main panel and the sub panel and the distribution. So all the schedules, all the calculations, everything you have to provide. Okay. Then standardized drawing symbol. In the North American market, the American National Standards Institute, or shortly known as ANSI, you might have heard about ANSI codes. You will be used to representing the relays, circuit breakers using these ANSI codes. So in cooperation with the Institute of Electrical and Electronics Engineers, that known as IEEE, has developed standardized drawing symbols and nomenclature to represent common devices represented on one lines, control schematics and other electrical drawings. For example, when you represent a transformer, this is a common legends, a common symbol. So there is a standard symbol. You cannot use your own symbol. You have to use the standard symbol for the transformer representation, for the circuit breaker, for the bus bars, for the cable. Cables will be represented as one line only. You will be mentioning the cable details along with that line. And relays, the potential transformer, and isolators. So you have to follow the standards. You cannot use your own symbols. Okay. The existing standard for North America, including the Canadian standard CSA C99, is IEEE 3151975, reaffirmed 1993, and CY32.9. This version recognizes electrical diagrams are a factor in international trade. The use of one common simple language for ensures a clear presentation and economical diagram preparation for a variety of users. Okay. Consequently, the standards coordinating committee has added various international electrotechnical commission symbols that are used in worldwide. If you want to see the symbols, you just can Google. You will get the symbols which is related to the equipments. So if you want to represent a transformer, you have to use the standard symbol. If you want to represent the circuit breakers, you have to use the standard symbol. Okay. And components in SLD. What will be the components which will come in the single line diagram, in the representation, also in the main panels or the sub panels? What all things will be there in the SLD? It will be having bus bars, cables, circuit breakers, current transformers, potential transformers, distribution transformers, generators, isolators, relays, capacitor banks, measuring equipments. All these components will be there in the SLD. Okay. Measuring equipments means current transformer used for for measuring purpose, like ammeter, voltmeter, frequency meter, energy meter. So that are the measuring equipments. Capacitor banks used for the improve the efficiency of the transformer, to improve the power factor. Okay. Relay means for the switching devices, for the circuit breaker, For switching the circuit breakers, we will be using earth fault relays, overcurrent relays, and the isolators. As you know, if the client requires a backup load, we might have to provide the generators and its schematic details. Again, the distribution transformer, the as per the standards of the country where you are following the or doing the project, you might have to provide independent transformers for your building according to the load. And the current transformers, again, current transformers are mainly used for measuring as well as protection. Okay, the circuit breakers, each panel will be having incoming and outgoing supply, where we will be providing the circuit breakers and the isolators. And the cables from the bus bars to the sub panel, we will be feeding the main panel and sub panel using the cables. Okay, these are the main components in SLD. So this is a typical flowchart of an SLD. If you're taking 11 kV supply, so the 11 kV supply is the HT side, high tension side. So it is coming to an 11 kV HT panel. So from the 11 kV from the local substation, like if you are staying in a particular state, or your area will be having a local substation, right? Maybe it will be a 66 kV or 33 kV. It will be having an 11 kV outgoing. This 11 kV outgoing is fed into different areas, and you will be taking this 11 kV supply from the nearest electrical post. And an 11 kV supply means a 1 3/4 coil of 95 square mm, maybe, or 150 square mm, or under, if it is underground cable, you might have to use a 300 square mm cable. So it will be coming through the trench or underground, or mounted on somewhere. You'll be feeding according to the permission you're getting from the authority. So this will be coming and entering to the 11 kV panel. So the 11 kV panel might be having a protective device, and the outgoing will be fed into a transformer or the 11 kV substation. 11 kV substation will be having a transformer, which might be an indoor type or an outdoor type. So this transformer will be having a rating of particular kVA according to our load, starting from 100 or 250 or 315 or 400, 500, whatever the load. So this transformer's rating, voltage rating is 11 kV bar 433 volt, which means the secondary side you are getting 433 volt. Okay, then this transformer will be having protection on the primary side as well as the secondary side. Okay, then from the secondary side, it will be fed to the main switchboard or the main distribution board. Okay, so the main distribution board or the main switchboard will be having a incomer. Either it will be MCCB or ACB, as per the demand we have to provide different breakers. So this breaker is provided for the entire MSB protection. So this MSB again subdivided into like SSB1, SSB2, SSB3, etc. So the SSB means sub switchboard. As I said before, you will not be directly taking all the loads from main switchboard. You will be providing main switchboard, sub switchboard, then only the final distribution board will be coming. So from the main switchboard, you might be having a number of sub switchboard. Maybe it will be according to your number of floors, or number of energy meters, or number of distribution boards. You are the one who is arranging the sub panels when we prepare this SLD. Okay. So the sub panel from the SSB1, SSB2, SSB3, you will be having certain final distribution boards. The final distribution board is the distribution board we see the, for a residential building, you can see in our building a particular distribution board. That is a final distribution board. From the distribution board, it is directly going to the switchboards, and from the switchboard directly going to the equipments. Okay, this is typical flowchart of an SLD. So the procedure for preparing the single line diagram. So load scheduling and load balancing. Those who have attended the previous webinar might have know the load scheduling and load balancing procedure. And next one is calculating the maximum demand, arranging the load as per the requirements, cable selection, selection of protective device as per the short circuit calculations, bus bar selection, arranging the sub panels, coordinating the sub panels with the main panel, and the transformer selection and the generator selection. So for preparing the single line diagram, you have to do all these things. Main important thing is like load scheduling. Load scheduling means uh, when you're doing a commercial building project or a residential building project, you will be having certain loads in the building, right? Lighting load, power loads, and the firefighting loads, HVC loads. Okay. So you'll be arranging these loads. You will be preparing the circuits as per the standards. You will be preparing light circuit, power circuits. Then you will be arranging distribution boards. When you arrange the distribution board, you have to do the load schedule. Then only you will get the rating, total connected load, everything. Okay. Then after getting all these details, you will be providing number of distribution boards. So according to the number of distribution board, you will be having each distribution will be mentioned with its total load and its maximum demand. Okay. So from that details, you will get an idea of number of sub panels, because if you are having 20 distribution boards, you cannot arrange it all together in a sub panel. You might have to go with 2 or 3 sub panels. If it is having 2 or 3 floors, you will be going with 2 or 3 sub panels. So you will get an idea of arranging these loads according to the project requirement. Okay. Then the cable size or cable selection for the each distribution boards and the sub panels. You have to do all these things. So in the single line diagram, you have to do all the calculation that is coming in the electrical system designing: lighting calculation, power calculation, the cable selection, and the circuit breaker selection. If the load is increasing above a particular limit, you have to select the transformer. And if the client is demanding for a backup, you have to select the generator and its protection, everything. Okay. These are the procedures for preparing the single line diagram. So this one is the load scheduling and load balancing. As I said before, you might have seen this load scheduling. This is represented as the equipment list will be shown in this list, and the room or area where these equipments are scheduled, and the unit wattages will be represented, and we will be balancing it as the three-phase load demands. Like you have to balance it. Okay, RYB should be at least 10% difference should be the maximum allowance is 10%, and RYB should be individually balanced, and you will get the total load also. So after doing the load calculation, you will get the total load of the entire building. Okay. Then after getting the total load, you need to calculate the maximum demand. So the calculation of maximum demand is total connected load divided by the diversity factor, or total connected load into demand factor. There are two factors. Some countries may be using only demand factor. Demand factor is like it will be less than 1. Okay, it's like a percentage of the demand we are using. Maximum demand is the peak load we are using at a time. Okay, so you will not design the transformer or the main incomer cables according to the total connected load, because you know this total connected load is all the connected load that is allowed in the allocated in the building. You will not use all the load at a time. That is why we are calculating the maximum demand. Okay, the diversity factor means it will be between 1 and 2. You can't take diversity factor more than 2. Okay, so if you're assuming diversity factor is 1.5, you have to divide the total connected load with that particular value. If it is 1.5, you have to divide the total connected load with the diversity factor. You will get the maximum demand. Either you can divide it with the diversity factor, or you can multiply it with the demand factor. Okay. So what is connected load? Connected load is the rating of the apparatus installed on consumer's premises. Okay, you will get to know that by calculating the individual equipment, all the equipments connected in your building, you will get the total connected load. And what is the maximum demand? Maximum demand is the maximum load which a consumer uses at any time. For example, the peak time, evening 6 to 10. For a residential building, the peak time is evening 6 to 10 or 6 to 11. You will be switching on all of your equipments, almost all 80% or 75% of equipments will be turned on. So that is the maximum demand. Okay. Then what is the demand factor? The ratio of the demand to the connected load is called the demand factor. Okay. The ratio of the average load to the maximum load is the load factor. And what is diversity factor? The ratio of the sum of the maximum demands of the individual consumers and the simultaneously maximum demand on the whole group during a particular time, that is called the diversity factor. Okay, so these are the definitions for diversity factor as well as demand factor. So then the cable selection, you might have seen the equation, right? We have studied this equation, P equal to root 3 VA cos phi. This is the equation of power in 3 phase. So you know the voltage is 415 or 433, and cos phi is considered as 0.8. So from this equation, if you know the connected load, you can calculate the current rating. So after getting the current rating, you will be adding the safety factors like 20% or 25%. And for the selection of cable, actually, you have to understand the method of cable installation. If it is underground, or if it is installed in air, or if it is in duct, you have to consider the derating factors also. Then only you can select the proper cable size. Then you will be having a cable chart, cable selection chart. For example, like this. This is a voltage drop and resistance of standard AYF cables. This is not from a particular brand. This is a general table. When you select a cable size, you have to make sure how it is installed. This method is known as clip direct. So you can see the cross-sectional area from 1.5 mm square to 400 square mm. And the current rating for single phase as well as three phase is represented. So when you get the current rating and you're adding the safety factor, you will get the final ampere. So from this final ampere, for example, if the ampere is 115, corresponding cable size is 50 square mm for the three phase. Okay, if it is 135, then it is 70. Okay, so after considering the derating factors, then only you should consider the total ampere. Then the most important thing is voltage drop. Voltage drop means like all the countries, like it is universally allowed, maximum allowance is 3%. For example, when you're supplying electric supply from main panel to sub panel, and the distance between main panel and sub panel is more than 100 meter. Just imagine more than 100 meter. And the supply side is 433 volt, and you have to make sure that the receiving side is less than, the drop is less than 3%. If the drop is more than 3%, it is not allowed. So you have to do the voltage drop calculation. Okay. Then the protective devices, like again the same equation, P equal to root 3 VA cos phi. If it is three phase, as you know, in single phase it is P equal to VA cos phi. Based on the rated current and short circuit current, you have to select the appropriate breaker. And also the fault current. While selecting the circuit breakers, one of the description is ampere and another one is kiloampere, the fault current value. So if you're assuming a fault level of 150 MVA, 250 MVA, according to the fault MVA, you have to calculate the fault current. Fault current equation is fault MVA into 10 raised to 3 divided by root 3 into kV. If the supply side is 11 kV, you have to take it as root 3 into 11. Okay. We have different types of, I have shown only few breakers. We have different types of breaker according to the demand. Usually when we do the MV system, medium voltage system, we select MCB, MCCB, ACB. MCB is miniature circuit breaker. MCCB is molded case circuit breaker. ACB is air circuit breaker. All these breakers have different range of operations. Okay. According to the requirement, we will be selecting the proper circuit breakers. And the bus bar selection, the panel board or the single line diagram we are representing or we are submitting into the government, it is a flow chart for the electrical load in the building. So how we are scheduling this load? It will be arranged in a panel board, right? So this panel board will be having bus bars. So you have to select the bus bars. Bus bar will be represented as width into thickness. You have to mention the width as well as thickness. So in this figure, you can see red, yellow, blue, because our color configuration is RYB configuration. That is why it is represented as red, yellow, blue. So, and also for the neutral link also you have to show a bus, and also for earth link also you have to show a bus. So you have to calculate the bus bar sizes also. So this is a standard bus bar chart. You can see this is for aluminum only. Switchboard rating up to 125 ampere. If it is up to 125 ampere, you can select 25 into 6. 25 is the width, 6 is the thickness. Okay, for the neutral also 25 into 6. Up to 200 ampere, 40 into 6, and there it goes. It will be increasing, and the number of runs also will be increasing according to the current demand. So the standard bus bar size also given below. Then this is how the 11 kV HT panel looks like. We provide a 11 kV panel. If you are having more than 2 or 3 transformer in a building, we will be providing 11 kV panel. This 11 kV panel will be having outgoings with the vacuum circuit breaker, HDLBSF unit, and the main incomer will be vacuum circuit breaker. So according to the project size or the total load, the panel size or panel schedule will be changing. So, okay, the transformer selection. So as I said before, you have to select the transformer based on the maximum demand, not on the connected load. Okay, so maximum demand you have to calculate. You know the calculation of maximum demand, total connected load into demand factor or total connected load divided by diversity factor. And you have to select the type of transformer also. If government is restricting, you have to use, you can use only indoor type. Then you have to select the indoor type transformer, or mentioned as USS, unitized substation. If it is an industrial project and if outdoor transformer is permissible, you can use the outdoor transformer. Okay, for using outdoor transformer, you have to follow certain procedures. Okay, then this is the standard size of transformer, 63 to 100. This is a small example of standard size, and the current rating also provided, and the recommended cable size also provided for 63 kVA. A2HF. A2HF means aluminum cable, XLP insulation, steel strip armored, PVC outer sheet. Okay, then the cable size is represented below. Okay, so these are the primary and secondary side protection for a transformer. If when you choose a transformer, here you can see the method of installation, the rating, the primary side protection and the secondary side protection. If you are taking an indoor transformer, you can see in the second row, up to and including 400 kVA indoor. The primary protection is 11 kV, ABSF unit, air brake switch fuse unit, or vacuum circuit breaker or gas circuit breaker, the 2 overcurrent and 1 earth fault relay, preferably with a DC trip. And the secondary protection is MCCB having duty and earth fault release and standby low set earth fault relay using CT or current transformer at neutral earthing conductor or air circuit breaker with proper current setting with 3 overcurrent and 1 earth. Either you can use ACB or MCCB. This is a recommended protection for the primary side and secondary side of a transformer up to or including 400 kVA. If the transformer size is greater than 400 kVA, you have to follow the next. You can see the third or fourth row. Then the protection has been changed, or the type of protection change. You have to use ACB draw type. You cannot use MCCB here. Okay. So these are the protection for the primary and secondary side of a transformer. So then the generator selection. Next one is the generator selection. If the total demand and the maximum demand calculation, like you are taking transformer size as for the maximum demand, right? So if the client is demanding a full backup load, no need to calculate the generator again, because the same calculation you have done for the transformer is you can be used for the generator. But if client is demanding a certain loads only, for example, if you're taking a hospital, you might not consider all the area. You will be giving importance to the critical areas, the operation theaters, so or and also etc. Like you will be having many important sections in the hospital. You will be considering that area only. From that area, you will be getting the backup load. So you will be arranging emergency DBs, and you will be arranging the schedule, and you will be having a generator switchboard separately for the generator. Okay, if the backup load is full backup, if the backup load is taking as full backup load, no need to do extra calculation. The same calculation we have done for the transformer, we can use for the generator. Okay, these are the standard rating of a generator and its protection. Starting from 5 kVA and 625, 750, 1000 kVA is mentioned in this table, and full load current is mentioned. So when you select the generator, after calculating the backup load and considering the safety factor, you will get a particular kVA. Then you will be looking for the standard rating above that kVA or equal to that kVA. Then from that company's or that particular company's catalog, they will be having the current rating and all details. So you have to provide the protection. And in this table, you can see MCB, MCCB is mentioned for the certain generators, and the generators above 100 kVA is having MCCB plus standby low set earth fault relay using CT. But generators up to 100, it is not mentioned for the earth fault relay and all. So according to the procedures or the inspectorate requirements, you have to do the calculations and the single line diagram arrangements. So this is how a 433 volt main switchboard looks like. You can see certain meters, indicators, ammeter, voltmeter, and the main incomer and the outgoings. Okay, and the panel board components. All the panel boards will be having relays, voltmeter, ammeter, LBSFU, that is load brake switch fuse unit, or the air brake switch fuse unit, CT, or the current transformers. Okay, and etc. Many other equipments will be there. And these are the commonly used legends to represent the circuit breakers, ammeter, everything. You can see 52 is the ANSI code for the draw out type circuit breaker. Ammeter, you can see the mentioning. Molded case circuit breaker, ammeter switch, ammeter selector switch, disconnection unit. All the legends have been represented. These are the standard legends we are using while we prepare a single line diagram. So all the details you have to mention in single line also. You have to use the proper legends. Okay, these are the legends. So here I have an example. We have a requirement, like we are doing a apartment project. The apartment project is in a compound we have 3 towers. Okay, 3 towers, and each tower is having 22 stories. And I have already calculated, or I have already given these values. Tower 1 is having 500 kVA transformer. Tower 2 is having 500 kVA transformer. Tower 3 is having 400 kVA transformer. So we have 3 transformers in the compound, usually for 3 towers. So how we will be preparing, or how we will be going through this single line diagram? So let us go to the single line diagram. Okay, you can see 11 kV supply. It is represented all in a line, single line. You can see this is represented as 3 into 300 square mm XLPE cable. So this is the main 11 kV cable, or 11 HT side cable that is coming to our compound. Okay, so as I represented the flow chart, it is directly going to the HT panel. So we have drawn a box. We have mentioned it as HT panel, and the HT panel having an incomer of 52. It is represented as 52. You can see the description. You can see the indicators on, off, trip. This is the indicators. So you have to mention every detail in the single line diagram. Okay. So this is 52. That means a draw-out breaker. The rating is 800 MVA. The fault level is 350 MVA. 12 kV vacuum circuit breaker with 3 overcurrent and 1 earth fault relay. So this is standard protection we are using for an HT panel. Okay. You can see current transformer over here, which is class 5P10 10 VA. So this is the current transformer rating, and this is the class. If you see 5P or 10P or whatever the term, you can, if you see the P letter, you have to understand that is used for protection. If it is used for measuring, you will not see the letter P. Okay. Then this is the bus bar, 11 kV, 900 ampere, 3-phase, 50 hertz, aluminum bus bar. So we have represented the bus bar size and the ampere, and the size we have mentioned here, aluminum bus bar, 15 to 10 mm aluminum bus bar. And this bus bar is having 1, 2, 3, 4, 5 outgoings. Okay, we have 3 towers, right? In our question, we have 3 towers. But in this diagram, we have 5 outgoings because 2 numbers is considered for the future. Okay, so the first rating is 630 ampere, 350 MVA, 11 kV HT LBSFU unit. So you might have seen in the presentation the secondary side protection of a transformer, LBSFU unit, ABSF unit. So this is the primary side protection inside the HT panel. Okay. Then from this HT panel, we have taken 3 into 150 square mm. Okay. 3 into 150 square mm cable. Okay. It might be 1 run of 3-core cable or 3 run of 150 square mm single core cable. Okay. So the total distance from the HT panel to the 11 kV substation or the unitized substation, it is 35 meter. So we have mentioned the cable specification and the distance between the HT panel and the sub panel. So this one is for the tower 1, and this one is for tower 2, and this one is for tower 3. Okay. So This one is known as USS because unitized substation, which is indoor type. So you can see the transformer representation as 500 kVA. Okay, the rating of transformer is given, the voltage ratio is given, and the type of transformer, dry type, cast resin, indoor, air cooled transformer. So this is the representation you are using for the transformers, like according to our standards, delta star configuration and 11 kV. Again, in the USS also, you can see the same protection which we have used in the HT panel. Okay, near to the USS. Okay, for the emergency turn off push button also provided. If you want to immediately turn off this transformer, you have a button to turn off this with the DC shunt trip. Okay, so all this as per the standards, all the details we have mentioned here. And from the transformer, from the 500 kVA transformer, another single line is going downwards, which is 3 into 3.5 core. 3 runs, that is the representation used for 3. 3 run means 3 number of cables. 3.5 C is 3.5 core cable. And the size of cable is 400 square mm. And the type of insulation and the conductor, it is mentioned AYFY. Okay, and the distance from the USS to the main panel is 5 meters. Okay, so you got a clarity, right? From the 11 kV line, it is coming to HT panel. HT panel is having 5 number of outgoings, which is connected only for 3, and 2 is for future. So the first one is for the electrical room, which is having USS unitized substation of 500 kVA. Second one also 500 kVA. It is typical because both tower have same load. And tower 3 is having a less load comparing to the tower 1 and 2. So it is 400 kVA. So all the other are same. Main HTLBSF unit are same, and the representation is same. Only the rating has been changed. Okay. So here 3 run-off cable, 3 run-off cable. Here only 2 run-off cable. Okay. And main incomer of the MSB is 800 ampere, 65 kiloampere, 4-pole, main draw out type ACB with 3 overcurrent and 1 earth fault release set at 670 ampere. So if you remember the primary and secondary side protection, you can see above 400 kVA, the type of protection is ACB draw out type with 3 overcurrent. And so as per this table, we have provided the specifications. Okay, so this is the MSB. ML is a representation of the tower. Okay, so this is a MSB. You can see the MSB's total load details, everything under. You can see the connected load in kilowatt and the pumps used and the capacity of the banks used and the total ampere and the cable size and the runs and the core, 3 run and 3.5 core, and the distance and the ampere and the earthing conductor size. Everything is mentioned in this cable. So from this diagram, you can see only the flowchart from the 11 kV panel to the main panel only. You have to elaborate this again. You have to elaborate this from the main panel to sub panel, then to the final distribution board. So this continues. Okay, you can see it is represented as unitized substation ML. Again, you can see unitized substation ML is represented here. It is again, to elaborate it again, we have represented it again here. Okay, from the unitized substation, again we have represented. Okay, then you can see the same 500 kV transformer, and here you can see the single line is coming downwards and the same 800. So this MSB is elaborated here. You can see only a box here. Here we have elaborated this with the bus bar details, the voltmeter, ammeters, everything. So in this MSB, what all components are coming? You can see a bus bar. To the bus bar, a cable is coming from the transformer. That is 3 into 3.5 core into 400 square mm AYFA cable. The distance between the USS and the MSB is 5 meter. You can see a voltage selector switch with voltmeter. It is ranging from 0 to 500 volt. And the breaker is 800 ampere, 65 kiloampere, 4-pole, main draw out type ACB, air circuit breaker, with 3 overcurrent and 1 earth fault relay, and plus shunt trip release set at 670 ampere. We have set this ampere according to the maximum rating of a transformer. 500 kVA transformer can give maximum 670. So if the MSB load is demanding a current above 670 ampere, this will be shut down. Okay. So for measuring, For ammeters, you can see a CT is provided. Before the ammeter, you can see a CT is provided, because when you represent an ammeter, you cannot directly connect this ammeter to the cables or the bus bars, because you see the rating, right? 800 ampere. There is no ammeter which you can measure 800 ampere. So you have to step down the current. So for that, you have selected a 800 bar 5 ampere class 1 10 VA. 10 VA is the burden, class is 1, and 800 bar 5A, because we have taken the main breaker as 800 ampere. So we have taken the primary rating of the CT as 800. From the CT, it is going to ammeter. So the ammeter range, it will be calculating the current as per the ratio, 800 bar 5 ratio. So you'll be seeing the, it might be an analog display or a digital display. Okay. Then the indicators. So in the main panel, you can see all these things: ammeter, voltmeter. So you have to represent everything that is coming in the main panel or the sub panel. You have to mention all the details in the SLD. You will be giving this to a contractor or a panel board manufacturer. He'll be manufacturing the panels or the main panel or the HT panel according to your single line diagram. So you have to make sure you have given all the details correctly. So here the bus bar size is 2 run of 50 into 10 mm aluminum, because we have taken the current as 800, right? As you can see in the slide, the bus bar size up to 800 is 2 into 50 into 10. Okay, up to 800 ampere. So since we have taken 800 ampere, you have taken the bus bar as 2 into 50 into 10. And for neutral, we will be taking only half, since neutral will not be carrying all the ampere which is running to the phase. Okay, then this MSB is for the tower 1. Okay, so as I said before, tower 1 is having 22 floors. So each floor is occupied with number of apartments, maybe 6 numbers or 7 numbers or 8 numbers. Okay, so we have to schedule. The scheduling is continuing, right? From the MSB, it is going to, we can see a 250 ampere MCCB outgoing, and again 250 ampere MCCB. Number of outgoings is like number of 3, 4, 5. You can see 6 outgoings in the MSB. Okay, so one of the outgoing is mentioned as PCC1. Okay, PCC1 means power control center. These are the short form. These are the standard short form we are using. If this panel is occupied with the motors, we will be mentioning it as MCC. That is motor control centers. Okay. So this PCC1 for the tower 1, you can see MP1. You can see 1, 2, 3, 4 outgoings. First outgoing is metering panel 1. Second outgoing is metering panel 2. And the third outgoing is metering panel 3. And the 4 outgoing is metering panel 4. So you might have you will not get an idea by seeing this SLD for the first time. I will explain that. So from this MSB, it is going to power control center. Okay. From the power control center, it is going to the metering panel. Okay. So there are 22 floors, right? If you are taking metering panel for each floor, metering panel means it will be having energy meter inside. For apartment, we have to provide energy meters, right? That is why it is called as metering panel. If you're taking metering panels for each floor, you might be having 22 or 21 metering panels. All these metering panels you cannot directly connect to the MSB, because the incomer rating of the MSB and the outgoing rate of the MSB should have a relation, 1/3 or 1/5. You cannot go down up to 1/3 or 1/5. So you have taken PCC1, PCC2, PCC3, PCC4. In this PCC1, you can see metering panel 1, metering panel 1, metering panel 2, metering panel 3, metering panel. In this PC or in this metering panel, you can see again some outgoings, that is LDB1, LDB2, LDB3, LDB4, LDB5, LDB6, LDB7. You can see 7 distribution boards are connected, 7 final distribution boards are connected to the metering panel. This metering panel is connected to the power control center. This power control center is connected to the MSB. Okay. So thereby it goes down. So you have to fill all the details of PCC1 and PCC2. And it will be like here you can see PCC4. For example, if you are taking PCC4, from PCC4, one of the outgoing is going to the metering panel 13, and it is 14, 15, 16. So as per the number of metering panel, the sub-panels will be increasing, and as per the sub-panels, you have to mention all the sub-panel with the connected load and the maximum demand. For MSB, we have mentioned here the connected load in kW. This is the motor load, and this is the capacitor load. And the maximum demand, you can see the maximum demand has become almost half. Okay, because this is a residential building. You can consider 1.5 as the diversity factor or 0.6 as the demand factor. That is why the maximum demand is very less. Okay. And these outgoings are having power control center, and each power control center is having certain metering panels. If you see the electrical room of this building, you can see this is the electrical room for the tower 1. Okay, we have arranged the HTLBSF unit and the 500 kVA US, and you can see PCC1. This is a panel. From PCC1, it is connected to metering panel 1 to 4. Then PCC3, PCC4, PCC5. All this panel will be PCC2. All this panel will be arranged in this particular electrical room for the tower 1 and tower 2, tower 3. So in this SLD, you can see MSBML, that is a tower 1. MSBAL, that is a tower 2. MSBMW, that is tower 3. Okay, we have developed all the details like the sub panels, the main panels, everything. Okay, so this is a typical arrangement of a single line diagram, and final distribution board will be looking like this. You can see the typical details of a common DBs. It is having from the common panel, it is coming to the 40 ampere, 4 pole, 30 milliampere RCBO. This is a final distribution board, which is represented as R phase, Y phase, B phase. This R phase will be having individual MCB breakers with 6 or 10 or 16 ampere breakers. Again, the Y phase also will be having 6 or 10 or 16. So all the details are included in this SLD. And as you can see, for all the 3 towers, we have selected only 500 kV generator. You have to consider tower 1, tower 2, tower 3. If you are taking full load, you have to take 500 kV generator for each towers. The client will not be willing to take 500 kV generator for each towers, because generator cost is very comparatively high from the transformer, and the backup load and the backup demand is coming like once in a week or once in a month. So no one will be taking the full load backup generator for an apartment building. So here they have taken 500 kV generator for all the 3 towers. You can see generator description, emergency off button, and the cable size coming from the generator. This is a generator control panel. In the generator control panel, you can see the connected load, the maximum demand, and the fire panel details. Again, the air circuit breaker and the protection earth fault relay, the load on switch indicator, energy meter. For energy meter also you have to use the CT. From the generator control panel, you can see the generator main switchboard. This is the one I have mentioned before, generator main switchboard. And from this generator main switchboard, you can see the first outgoing as 400 TPN isolator. All these are breakers, MCCB breakers. This one is a isolator. Isolator is simple as known as a switch, isolating switch, because this one is going to the fire panel. If in case any high load is coming, if you are placing MCCB in accidentally, it might get tripped. That is why we are not using breakers in the breakers for the fire panel, only isolator. Remaining panel, you can see this one is fire panel for the first outgoing, and the second outgoing is common panel. All the details, all the connected details are given below. Okay, the rating is given in kilowatt plus HP. The voltage values given here. You can see the connected load here, rated current in amperes, the size, the number of runs or core, and the length in meters, and earth conductor size, everything. Okay. So this is an example of apartment building of 3 towers with 22 floors. This is the apartment. Okay. So if you're doing a small residential project, it will be having only 2 or 3 dBs. So the main incomer will be energy meter. From the energy meter, you will be having a main panel. It might be a VTP and distribution board or a bus bar panel. From the bus bar panel, you might have only 2 or 3 outgoings and 1 spare. If it is a small residential building, this is a big project. That is why the facility is little bit complicated. Okay, so you can see the HT panel, USS, and the USS is again elaborated here to the PCC panels, power control centers. From the PCC, you can see the metering panel, and from the metering panel, you can see the distribution boards, and from the distribution boards, you can see the final single line diagram. Okay, so these are the typical representation of a SLD, and you can see the common panel or the lift panel. These panels will have backup from the diesel generator because these are commonly used areas, lift and the common areas like lobby, car parking. So from the common panel, you have again sub connections. That is lift panel. You can see the from common panel for the lift panel for the different connections, and you can see lift motor of 7.5 HP and lift DB. From the lift panel, you can see a lift motor as well as a lift DB connection. And again, from the common panel, there is a STP DB, sewage treatment plants, distribution boards. From the sewage treatment plant panel board, you can see different outgoings for different motors, filter, feed pump. You have different pump. That is why we have already told before we have to coordinate with the other mechanical related like HVAC or plumbing. They will be providing all these details. So you have to arrange this in our SLD. Okay, and this lift DB is again elaborated here. You can see 8-way SPN MCBDB. This is the representation of a single pole neutral, that is single phase DB. Connected load, maximum demand, all the details are given here. And typical details of LDBs are given here. Okay, so all the details will be coming in the single line diagram presentation. So once we submit the drawing to the contractor or the for approval, the person who is viewing this SLD, who is studying this SLD, will get idea about the total demand, how the load is flowing, how much number of circuit breakers, sub panels, and after preparing this panel boards or the sub panels, we will get an idea of the electrical rooms also, how to arrange these panels according to, if the architecture is not providing sufficient area for the MEP services or the electrical room, you have to recommend the architect to increase the room size. You have to provide generators, transformers, this much panels. So all this to be accommodated into an electrical room. Okay, so after preparing the SLD only, you will get an idea of the electrical room size, the panel board size, and the details and all. So how this MSB is looks like is the general arrangement of typical flats 1 and 2. You can see this is a GA drawing, general arrangement drawing. You can see the ammeter, voltmeter, voltage selector switch, the indicators, the energy meter, the bus bar chamber, and the main incomer. So the main incomer is here. You can see the main incomer, and you can see the bus bar chamber in between, energy meter, and you have, as we have mentioned, is having 3 sits 250 ampere outgoings. You can see that. 1, 2, 3, 4, 5, 6. You can see 6 outgoings. This representations GA drawing, that is general arrangement drawing, is given below. Okay. So for preparing SLD, we have to initially start with the load calculation. After load calculation, you will get the total load. Then after the total load, you will get the maximum demand. Then you will get an idea of the transformer size. Then if it is an apartment project, you will get an idea of metering panels, because for each floor you will be considering metering panels. If there is 20 floors, you have 20 metering panels. So for example, you cannot directly connect all this metering panel to the main panels, because the outgoing rating will be very less comparing to the income rating. So we will be considering 4 or 5 PCC panels, power control center. From these PCC panels, we will be providing the metering panel. So initially you will be struggling to do the SLD drawing, but later on, like when you do 2 or 3 projects, you get an idea how to do this single line diagram or how to arrange these loads. Okay, and how to mention all the details. You have to mention everything, like cable details, circuit breaker details, and the generator sizing, generators protection, everything. Okay, so I think you have got some idea about the single line diagram and how to prepare this diagram. So I want you to do a calculation. I have an example. So this is a question for you all to calculate the total connected load, maximum demand, and the transformer size. So we have different motors and miscellaneous load and lighting loads. So you have 150 HP motor, that is 1 numbers, 250 HP motors, that is 9 numbers, 15 HP motors, that is 6 numbers. This is a random load. I'm just giving an example. This is a random load. When you do a project, you will have a specific requirement. Here we are giving random loads. And 10 HP motors, 3 numbers, 7.5 HP, 6 numbers. 5 HP, 7 numbers, 3 HP, 3 numbers, 2 HP, 3 numbers. And the miscellaneous loading, 15 kilowatt, lighting load, 15 kilowatt. So all the load details are given. So I want everyone to do the calculation. I want everyone to do calculate the total connected load and its maximum demand and the transformer size. For those who don't know the transformer standard size, I will show the table, but you can do the calculation. It's simple mathematics. Like you only need to convert the HP to kilowatt. 1 HP is 0.746 kilowatt or 746 watts. So you can do that conversion. Okay, you can take your time. I will give 5 to 10 minutes. You can do the calculation. I want everyone to do the calculation and give the total connected load, maximum demand. For calculating the maximum demand, I have already mentioned, assume diversity factor as 1.5. So you just need to you just need to divide the total connected load with 1.5. So you'll get the maximum demand. So from the maximum demand, you can select the standard size of transformer. Please do the calculation. You can give answer in the chat box. Initially, you have to convert the you can calculate all the motor loads. Then you need to convert into kilowatt. That is 1 HP is 0.746 kilowatt. So after converting, you have miscellaneous load and lighting load. You have to add with it. That is a total connect load. Okay. Then after getting total connect load, you have to divide it with diversity factor, because I have already given the diversity factor. So that value is the maximum demand. Then you have to add the safety factor also, 20% or 25%. You can add safety factor from the maximum demand. Then we will be selecting the transformer size. Those who want the standard table for transformer, I will show that. The chat box is open. You can do the calculation and you can give answer. If you have any doubts, you can ask. This is very simple. You have to just add all the motor loads, just multiply and add the motor loads, convert into the kilowatt. For converting, 1 HP is 0.746 kilowatt. Then add the miscellaneous load and lighting load together, you will get the total connected load. Then divide it with 1.5, you will get the maximum demand. Then you can add 20% safety factor. Then we will select the transformer. I want someone to do the calculation. I believe it is very simple. All of you can do, just multiply the value, add it and multiply the value to kilowatt, then add it, you will get the total connected load. We will have a session for clearing the doubts after this. Right now, I request all you to do the calculation. 200 kV is not the right answer. You have to do the calculation again because 150 HP one number, 25 HP 9 numbers, 15 HP 6 numbers. You have to multiply all the values like 150 into 1 plus 25 into 9. I think you are just adding 150 HP only. You have 9 numbers, 6 numbers, 3 numbers. Initially, you have to multiply it. Then only you will get the total connected load. 192.34, it's not the correct value. It's like 150 into 1 plus 25 into 9 plus 15 into 6 plus 10 into 3 by adding all the motors. I'm waiting for someone more to answer. I believe everyone can see the question, right? maximum demand. Three 359.49 is the total connected load or the maximum demand. Total kilowatt 433 kilowatt, maximum demand 268 kilowatt. Okay. Anybody want the transformer table so that you can tell the expected transformer size? Maximum demand 570. You have to make sure that total connected load, the maximum demand will be always less than the total connected load. I can see 502 kilowatt and maximum demand as 753. Maximum demand will be always less than the total connected load. Okay. What will be the transformer size? How you will be calculating the transformer size? Transformer size is in kVA, right? How you do the transformer calculation? We have to divide it with a 0.8. So can you give me the power factor is 0.8? Yeah. Divide the maximum demand with the power factor. Okay. Anyway, I will show the exact calculations. I'll show the exact calculation. You can see 150 HP 1 numbers, 25 HP 9 numbers, 15 HP 6 numbers, and 10 HP 3 numbers, 7.5 HP 6 numbers, 5 HP 7 numbers, and the total connected load is 590 HP plus 30 kilowatt. Okay, we have assumed the diversity factor as 1.5. Okay, okay. Then we'll be getting, after considering the maximum demand and the diversity factor in kVA, we'll be getting the size as 392 kVA. Okay. Then from this 392 kVA, how you got 392 kVA? Like after adding the HP load, motor load and the miscellaneous load and lighting load, you'll be getting 587.5 kVA as the total connect load. How you got this 587.5? By dividing it with 0.8. Then assuming the diversity factor, you'll be dividing it with 1.5. So you got it as 392 kVA. Okay. Then you have to add the safety factor. 20% is the safety factor. So after adding safety factor, you get 470.4 kVA as the final value. So the nearest transformer size is 500 kVA. So from this load, you have to add all the motor loads and you have to convert into kilowatt. Then you have to calculate the maximum demand. After maximum demand, you have to add a safety factor. Then divide it with 0.8 to get in kVA. So when you get in kVA, it is 470.4 kVA. and the nearest transformer is 500 kVA. Okay, so I will show how this single line diagram is represented. So this is how the single line diagram is represented. This is how the single line diagram is represented. 11 kV supply is coming and the HT panel. As you have seen in the previous diagram, you can see the HT panel. And from the HT panel, you can see LBSF unit, and it is directly connected to the transformer. Okay, you can see 500 kVA, oil natural, air natural transformer. It is indoor type. From the transformer, you can see it is connected to MSB. Okay, so you have to arrange the motors according to the load scheduling. Like we have a 150 HP motor, right? Then remaining all motors are 25 HP, 10 HP, 7.5 HP. So here we have directly connected the 150 HP motor to the MSP. You can see it. Okay, with a 400 ampere MCCB 35 kilo ampere rating set at 320 ampere. And next outgoing is again a 250 ampere breaker, which is mentioned as SSB1. So what all loads will be coming in the SSB1? SSB1, MCC1, MCC2, and capacitor panel, and you can see spare. Okay, in SSB1, what all load will be coming? The remaining motor loads. Okay, you can see the SSB1. In SSB1, you can see two spare and 1, 2, 3, 4, 5, 6 motors and some miscellaneous load and vertical DB connection. You can see it. Okay, so from the SSB1, first motor is 25 HP, next motor is 25 HP. So you can see 25 HP motors, 3 numbers in the SSB1. And the 15 HP motors, 2 numbers, 10 HP motors, 1 numbers. And you can see a VDB which is having all lesser pumps that is connected directly to the VDB, that is 30 HP. And again, the miscellaneous load or the lighting load is connected here to make sure that we are reaching approximately 145 HP plus 15 kilowatt, because since we have connected 150 HP motor directly to the MSP, we are trying to balance or trying to make sure that all are equally divided, the outgoings. So it is 150 HP, this is 145 HP plus 15 kilowatt, and MCC1 also 145 HP plus 15 kilowatt, and you have another outgoings MCC2. This is how we distribute a random number of loads like motors and miscellaneous load and lighting load. You can see all the connections here. SSB1, VDB1 and 2, and the VDB1 is having 7.5 HP motor 2 numbers, 5 HP 2 numbers, 3 HP 1 number, 2 HP. That is how we are getting that 30 HP load. In the lighting DB, you can see 15 kilowatt load that is distributed into 3 LDBs, 5 kilowatt, 5 kilowatt, 5 kilowatt. Okay. So if you're getting a random load, and you are asked to do single line diagram calculation, you have to do this way. You have to balance it. If it is a real project, if it is an apartment project, or if it's a specific industrial or commercial project, you can do according to the design parameters. Okay. So this is how we do the SLD calculation and single line diagram. So I hope everyone is clear regarding the single line diagram preparation. If you have any doubts, you can ask in the chat box. If you have any doubts regarding this calculation or regarding the previous apartment calculation or regarding this total presentation, you can ask doubts. Yeah, voltage drop calculation, you can ask me. The voltage drop calculation, right? Okay. You can ask me. I have taken the voltage drop chart.
Hello, sir.
Hello. Hello. You can unmute yourself and you can ask a doubt. Hello, I am not audible. Hello. Hello.
Those who want to speak, they can unmute their audio and they can speak if they have some doubts.
Okay. Hello.
Hello.
Okay, sir. I have a doubt. If I have to calculate the voltage drop of
Ah,
2 run of 185 mm square,
okay.
there is a dash, right?
We have a voltage drop value for the 185 square mm of one run, right?
Okay.
Okay, so you can assume that you can take that value and you can just divide by doing the 185 square mm. You can divide with 2.
Okay. If I need to calculate 3 into 185, so
The
what to
voltage drop
do?
will be very less, so you can just divide it with the 3.
3. Okay. Apo, sorry. Divided by number of turns.
Yeah,
Number of runs.
number of runs.
Okay,
Yeah.
okay, okay, okay. Okay, thank you, sir.
Okay. Is any what is the provision
Hello,
of the
sir.
case? Yeah. Hello.
നമ്മൾ ജനറേറ്ററിന്റെ ഒരു ഇതെടുത്ത് ചാർട്ട് എടുത്തില്ലേ,
Generator. Okay.
അതില് കോപ്പർ കണ്ടക്ടർ 25x3 എന്ന് പറഞ്ഞ പ്ലേറ്റ്, കോപ്പർ പ്ലേറ്റ് അർത്തിങ് ആണോ അത്?
Stripper thing. Ade.
സ്ട്രിപ്പ് അർത്തിങ് അല്ലേ?
Ade.
അതില് പാനൽ മീറ്റേഴ്സ് AM VM FM അതൊക്കെ എന്താ?
അതൊക്കെ അമ്മീറ്റർ, വോൾട്ട് മീറ്റർ, ഫ്രീക്വൻസി മീറ്റർ, എനർജി മീറ്റർ ആണ്. അതായത്
എനർജി മീറ്റർ.
ഞാൻ കാണിക്കാം. Okay. So from the generator size from 100 to 400 kV, you can see MCCB. The protection is MCCB plus standby low set earth fault relay using CT in neutral thing. This is a protective measures for the generators 100 to 400, and these are the panel meters: ammeter, voltmeter, frequency meter, and energy meter.
എനർജി മീറ്റർ. പിന്നെ 200 KVA ജനറേറ്ററിൽ 2x120 പറയുമ്പോ അതെന്താ വരുന്നത്?
2 run of 120 square mm cable. For 200 kVA generator, the recommended size is mentioned as 2 run of 120 square mm cable, or you can take cable size corresponding to the 280 amperes. From a catalog, you can take 280 ampere is the rated current. This is general table. If you take a particular brand like Caterpillar or any other Volvo, if you take any other brand, you can see the rated current. According to the rated current, you need to take the appropriate cable size. This is mentioned as 2 run into 120 square mm.
ഓക്കെ.
For calculating the derating factors, is like taking finding out the conditions where we are using the cables. If you are using it in the cable with a panel cable tray and you have a number of cables together, you have to calculate the grouping factor. Grouping factor is calculated based on the number of cables and the type of installation method. There is a chart in BS 7671. If you download BS 7671 PDF, you can get these derating values depending on the room temperatures and conditions, and ambient temperature condition, thickness of insulation, and grouping factors.
Okay,
So
sir.
there is a calculation based on derating factors. You have to divide the current again with the derating factors. Then only we will getting the final current. What all factors will be affecting the cable's rating? You have to calculate the derating factor. What is the provision for? Provision for KSEB ceiling means KSEB means it is Kerala State Electricity Board. So we need to provide provision for their ceiling, like their meters and arrangements, TOD meters. That is the provisions. It will be varying according to different government or different inspectorates. DG is standby. DG will be standby. Will be only using when it is required or when a firefighting occurs. We are actually recording this presentation in our Facebook page. You can actually view that after completing this session. It will be published in our Facebook page. So all this chart and all the slides you can see in our Facebook page. Our Facebook page will be link will be shared at the end of session.
Yeah. So thank you, students. I think you all have understood the topics that has been taken today, and you know that we have basically deals with the projects as well as the trained students. We have more than 15 years of experience in both training as well as in projects oriented. We are basically MVP consultants. More than 15,000 students have been successfully passed out from our institute. So, like if our services are in HVAC, electrical, plumbing, firefighting, etc. So, if some students are interested in joining some courses regarding this MEP, you can contact us. Like we have online platform also, so we do take we do take classes for different students who is been experienced as well as fresher students also. So those who are interested in studying these courses related to electrical or firefighting or plumbing or HVACs, you can contact us. So we have provided platform both in Zoom as well as in Skype. So if you are interested, you can attend our courses. So thank you everyone. So one more thing, like the feedback form will be posted in the chat box, and it will be available only for 60 minutes. And this link won't be published in the WhatsApp group. So kindly you have to click the link here, and you have to fill the feedback form. So I repeat, this won't be pasted or forwarded in the WhatsApp group. This will be available only in this chat box, and it will be valid only for 1 hour. So I request everyone to click and fill the feedback form so that you may get the e-certificate for the current webinar. So I have posted the Google form in the chat box. So kindly everyone click and fill the form. Thank you. So we would like to thank each one of the participants who has participated in this webinar, and I thank Mr. Akhil for taking this presentation well. Thank you everyone. Thank you. Have a good day.